Bismillahirrahmanirrahim. Assalamu alaikum, dear students. This is our next problem. Problem number 32. Okay. Fluid mechanics. Problem number 32. As usual, we first come to our statement. Oceans on Mars. Scientists have found evidence that Mars may once have had an ocean 0.500 kilometer deep. Okay. Dear students, we are not primarily concerned with kilometer, so we will have to convert this into meter, that is 500 meter. Okay. The acceleration due to gravity on Mars is 3.71 meter per second square. Okay. Acceleration due to gravity on surface of the earth is 9.8 meter per second square, but acceleration due to gravity on Mars is enough less than acceleration due to gravity on surface of the earth, which is 9.8, because 3.71 is almost one third of approximately 9.8. Okay. Part A of this problem is, what would be the gauge pressure at the bottom of such an ocean, assuming it was fresh water? Okay. So, dear students, here one thing more becomes relevant. Okay. Prior to this, one thing which has become relevant is that acceleration due to gravity on surface of the earth is 9.8 meter per second square, while the acceleration due to gravity on Mars is about one third of that. Okay. So, both these values will be considered in our problem. Okay. That is to say, acceleration due to gravity on the surface of the earth, that is 9.8 meter per second square, will also be used, and this value, that is 3.71 meter per second square, will also be used. The next thing to be pointed out is that, dear students, in this problem we will have to deal with two densities. Okay. Because in part A it is given that we have to assume water to be fresh water. Okay. While ocean is under consideration, so definitely density of seawater and density of fresh water both will be used in this problem. Okay. What I have said that two acceleration due to gravity and two densities of water are likely to be applicable in the solution of this problem. Okay. Part B, to what depth would you need to go in the Earth's ocean to experience the same gauge pressure? Okay. So, dear students, as I have said that first we move to table of densities, from where we see which two densities we will adopt in this problem. Okay. So, this is the table. Okay. Left column 1, 2, 3, 4, 5 and 6. Row number 5 and row number 6 of left column of this table deal with density of water and density of seawater. Okay. So, dear students, no doubt here the word fresh has not been used. We will assume first density to be the density of fresh water, while second density to be the density of seawater. Okay. So, what we will use density of water will be taken as 1000 kilogram per meter cube. Okay. and density of seawater will be taken as 1030 kilogram per meter cube. Okay, I think it is okay. Okay, this table will also be used to some extent, but dear students, use of this table will be almost optional. Okay, because we have to find pressure or gauge pressure. We have not been restricted to find the pressure both in Pascal and atmosphere. Okay, but as a matter of discretion, we will find that pressure both in Pascal as well as atmosphere, as we have done in the previous problem. Okay, so now we move to our solution in a formal manner. Okay, part A. We know that the pressure in a fluid at rest varies with depth h in the fluid according to the expression P equal to P naught plus rho g h, equation number 1, where P naught is the pressure at h equal to 0 and rho is the density of the fluid assumed uniform. Okay, rearranging equation 1 as P minus P naught equal to rho g h. Okay, quite clear. When P naught will be shifted on left side of equality, then it will become P minus P naught equal to rho g h. Okay, P minus P naught equal to rho g h, and using rho equal to 1000 kilogram per meter cube density of fresh water. Okay, dear students, in the table word fresh has not been used, only word water has been used, while in the next row of that table seawater, density of seawater is used. Okay, so in this part, that is part A, we will take density as that of density of fresh water, that is 1000 kilogram per meter cube, and acceleration due to gravity, we will not take the acceleration due to gravity on surface of the earth. We will take acceleration due to gravity on Mars, which is provided in the statement. Okay, the third thing is the height h, which is given in kilometer, but we have converted here we have converted kilometer into meter, so h has become 500 meter. Okay, putting all these three values in equation 1 after having been rearranged as in this form. Okay, so we get P minus P naught equal to value of rho into value of g into value of h is alternatively becomes equal to 1855000 kilogram per meter second square, and we know from definition of Pascal that 1 Pascal is equal to kilogram per meter second square, or alternatively it can also be written as Newton per meter square. Okay, so our answer is has become 1855000 Pascal. Okay, so to this extent 1855000 Pascal, our solution to the extent of part A has been absolutely solved. Okay, however, as a matter of discretion, we are now writing this figure in slightly different shapes as a matter of discretion. Okay, it is not necessary. So dear students, when we write it in this form, that is 1.855, then we will write it as 10 raised to the power 6 into 10 raised to the power 6 Pascal. Okay, when we write this figure as 18.55, then we will write it as into 10 raised to the power 5 Pascal. When we write this figure as 185.5, then we will write it as into 10 raised to the power 4 Pascal. Okay, similarly, when we write it as 1855, then we will write it as 10 raised to the into 10 raised to the power 3 Pascal. Okay, and we know that 10 raised to the power 3 is equal to kilo K, so it can alternatively be written as kilopascal. 1855 kilopascal. Okay, all these steps are quite optional. These are just matter of discretion. We are not bound to follow these steps. Okay, dear students, in the next step, what we have done, we have tried to express this pressure not only in Pascal but also in atmosphere. Okay, that is why we have divided that figure by 103 okay, so in this way it will be converted into atmosphere. Okay, hence our result becomes in shape of atmosphere equal to 18.31 atmosphere. Okay, here is the situation, dear students. Okay, 1 atmosphere is equal to 1.013 into 10 raised to the power 5 Pascal. Okay, if we remove this 10 raised to the power 5, then it will be written as 1 atmosphere is equal to 101300 Pascal. Okay, so many Pascal are equal to 1 atmosphere. 1 Pascal will be equal to 1 divided by 101300. Okay, and hence so many Pascal will be equal to this into this. Okay, so 18.31 atmosphere, part A has come to an end. Okay, now we come towards part B. Rearranging equation 1 as P minus P naught equal to rho g and using. Okay, to the extent of this first line, there is no difference in part A and part B. Difference begins from the second row of this slide or page. Okay, so what is the difference? Dear students, the difference is that in part A we had used density equal to 1000 kilogram per meter cube, which was the density of fresh water, but this is the density of sea water because ocean is involved. Okay, ocean, sea water, saltish water, similar expressions, similar concept. Okay, moreover, in previous part we had taken value of acceleration due to gravity on Mars, which was about 1/3 of this value. Okay, but here we are taking standard value. Okay, the third value which is h, this parameter is going to be determined. Okay, so here we can write it as a matter of discretion that h equal to sign of interrogation. Okay, but I have not written, so it is quite okay. Whether we write here that h is equal to sign of interrogation, which means that height h is to be determined, or even if we do not write h equal to sign of interrogation, it is quite okay. Okay, so we get what we get. We put all these values. Dear students, P minus P naught we have calculated in part A. Okay, so in part A, P minus P naught, here we can use any of these values. Okay, it is a matter of discretion for us. Okay, which of these alternate values we take. We have taken this value P minus P naught equal to so many Pascal in equal to this density of seawater into acceleration due to gravity on surface of the earth. Okay, this implies that here what we have done, we have written Pascal in shape of kilogram per meter second square, because Pascal is equal to kilogram per meter second square, so we can replace Pascal PA by kilogram per meter second square. Moreover, we have multiplied these two quantities. Okay, that is this is about 1000 and this is about 10, so 10,000 approximately, quite okay, and hence meter will be subtracted from meter cube, and in the denominator we will be left with meter square. Moreover, second scale will remain in the denominator, and kg into h will become in the numerator on the right hand side. Okay, this implies that h becomes equal to this quantity divided by this quantity into meter, because dear students, here we can, as a justifying step, we can say that dividing both sides by kilogram is eliminated. Moreover, we can say that multiplying both sides by second square is eliminated. Moreover, we can say that multiplying with meter, on left hand side m will be eliminated, and on right hand side simple m will remain in the denominator, and this m will be shifted on other side of equality and will become in the numerator. Okay, so in short, h has become equal to this figure over this figure, meter. This implies that h has become equal to 183.77 meter, and this is the end of our part B. Next, we have discussed this table, that this table was just used on optional basis in order to convert Pascal into atmosphere, and this table was used to find out the density of fresh water as well as sea water. And this is the end of this problem, and now we move to reference book. Reference book is Sears and Zemanski's University Physics with Modern Physics. Authors are Hug, D. Young, Roger A. Friedman, A. Lewis Ford. Its publisher is Pearson. Its 14th edition having been published in 2016, or 15th edition having been published in 2020 has been adopted or followed. And here chapter number 12 under title Fluid Mechanics is our relevant or concerned chapter, and this problem has been enumerated at serial number 9 of the exercise given at the end of this chapter, that is to say exercise number 12.9, and this is the end of our problem. Okay.